Hello students, how are you all? Welcome to the new session. In the last video we have discussed about crystal field theory, crystal field splitting in octahedral complexes we have discussed. Octahedral means coordination number 6, 6 ligands approached. Obviously degeneracy of d orbitals will be gone, split up into T2Z as well as EZ. The same thing will be happened in tetrahedral complexes also. So in this session, we'll discuss about crystal field splitting in tetrahedral complexes. Coordination number is equal to 4. So coordination number 4 means 4 unidentate ligands are surrounded by the central metal atom. Then while approaching the ligands to the central metal atom, obviously repulsions between the metal atom electrons and the ligand electrons. That repulsions leads to the splitting of degenerate d orbitals in metal atom into EZ and T2Z. Same thing which is happened in the octahedral will be happened here. Now 4 ligands approach to the central atom. Ligands approach to the central atom due to the repulsions between the ligand and metal electrons. There is a splitting of d orbitals. The splitting of degenerate d orbitals in tetrahedral complexes in presence of ligands called crystal field splitting in tetrahedral complexes. Now, it is different from that of octahedral complexes. So we'll write these points one by one. First point, in tetrahedral complexes, 4 ligands, central metal atom surrounded by metal atom. It is central atom surrounded by how many ligands totally? 4 ligands. When ligands approached to central atom, there is a repulsion between ligands electron and central atom. It is metal atom electrons. This repulsion causes splitting of d orbitals in tetrahedral complexes. This results splitting of degenerate d orbitals in presence of ligands, 4 ligands, splitting of degenerate d orbitals in presence of ligands. This is called crystal field splitting in tetrahedral complexes. This is indicated by delta T. In octahedral complexes indicated as delta O. Here delta T. Crystal field splitting in tetrahedral complexes. the splitting in tetrahedral complexes is different from that of octahedral complexes, It is different. In octahedral complex, lower is T2Z, higher is EZ. But in tetrahedral complexes, lower is EZ, higher is T2Z. We'll draw the diagram now for this. Okay, students, this is the diagram for crystal field splitting in tetrahedral complexes. Same like octahedral, little variation. So these are the degenerate d orbitals in free metal atom. So dxy, dyz, dzx, dx square minus y square, dz square. We have written already 5 degenerate orbitals. When ligands approached, 4 ligands, then obviously these are the 4 ligands approached in tetrahedral fashion. Obviously it has a little more energy due to the spherical symmetrical crystal field. Average energy of d orbitals of spherical crystal field. Then ligands approaching towards the metal atom, obviously repulsion starts. So after repulsion, it will be divided into 2 sets. One is EZ, another one is T2Z. Here we are using a word E only, not EZ. T2 only, but not which one? T2Z. Why? Reason? Because G subscript used only for octahedral and square planar complexes in which there is a center of symmetry. But there is no center of symmetry in which one? That is tetrahedral complexes. That's why we are not using a subscript called G. Clear it is? Here why we are using? I am writing here the reason. G subscript not used for tetrahedral complexes. Not used for tetrahedral complexes due to lack of center of symmetry. G subscript is not used for tetrahedral complexes due to lack of center of symmetry. Clear it is? So now it is only used for G subscript, only used for octahedral complexes and square planar complexes in which center of symmetry present. Reason that is. So we should use T2 as well as E. E is lower, T2 is higher, as I discussed in the last class. T2 is lower because of low repulsions. Similarly here, E lower because of low repulsions, because electron cloud direction is different from that of E orbitals, nothing but dx square minus y square and z square in tetrahedral complexes. That's why different means less repulsions. That's why E orbitals, these two will be in the lower energy. T2Z orbitals, T2 orbitals are higher energy because dxy, yz, zx orbitals direction is same to that of which one? Similar to that of ligand direction. In which complex is tetrahedral? Because of tetrahedral geometry. Diagrams are there? No need. Just reason. Enough. So this will be higher energy. This will be lower energy. This will be 3 by 5 times to that of delta T. This will be 2 by 5 times to that of delta T. So here, this is the diagram which represents the crystal field splitting in tetrahedral complexes. Okay. Students, as per the diagram, in octahedral complexes, T2Z downside 3, easy upside. But in tetrahedral complexes, it is reverse. Because of that is octahedral arrangement of ligands different, it is tetrahedral arrangement of ligands different. The reason behind is as I told you just now. So easy orbitals and the ligand approaching direction is different, less repulsions and lower energy. The T2Z orbitals dx, y, yz, zx and orbitals are approached in the direction of ligand, obviously more repulsions, higher in energy in tetrahedral complexes because of arrangement of or structure, tetrahedral structure. Now, the next one is important one. The splitting energy in tetrahedral and octahedral complexes, if you compare, delta T is equal to delta naught. So here the formula is 4 by 9 times to that of delta naught. This formula is very, very important. This is experimentally determined. In octahedral complexes, 6 ligands are there, obviously more 6 repulsions. In tetrahedral complexes, only 4 ligands, only 4 repulsions. 6 ligands means more number, more repulsions. 4 ligands means less number, less repulsions. Clear it is? So, based on that, simply, it can be written as delta T equal to 4, it means 0.45 it is, right? Times to that of delta naught. By this relation, you can say that if it is 0.45 into 2, just imagine 2, then you get how much? 0.9. This is 2, this is 0.9. Which is higher? 2 higher than 0.9. It means delta naught is higher than that of delta T by this information. It means delta naught higher than that of delta T by this formula. Simply delta T less than that of, what is that? Delta naught. The meaning is the splitting energy in tetrahedral complex is less than that of splitting energy in octahedral complex. Splitting energy less means opposite one is a pairing energy. P we have discussed in the last video. So splitting energy less, obviously pairing energy more. Splitting energy more, obviously pairing energy will be less. Then it means in tetrahedral complexes, splitting energy is less than that of which energy? That is pairing energy. Splitting energy low means pairing energy is high. Pairing energy high means high energy is required to pair electrons. First electron, to pair electron, more energy required. To pair electron, more energy required. Clear it is? More energy means difficult to pair. Difficult to pair means electrons will be entered into higher energy levels. Clear it is. How difficult to pair means all are unpaired electrons only. Obviously plus half, plus half, plus half, plus half. That indicates high spin only. It means in tetrahedral complexes, high spin complexes only possible. Low spin complexes are very rare. Why? A very, very important question. The reason behind is in tetrahedral complexes, delta T is 4 by 9 times to that of delta naught. Delta T is less than that of which one? Delta naught. The splitting energy of tetrahedral complex less than that of octahedral complex. That indicates pairing energy is more in tetrahedral complexes. Difficult to pair. It means all electrons are unpaired only. Unpaired means plus half, plus half, plus half. Such plus halves increases, spin also increases. That's why high spin complexes only possible, but not low spin complexes. Write that matter. Delta naught less than P means pairing energy is high than splitting energy. Then it means more energy is required to pair electron. More energy is required to pair electrons. It means first electron, okay. Second electron, okay. Third electron, difficult to pair because pairing energy is more entered into here. It means plus half, plus half, plus half. Spin will be increased. That's why it is a high spin complex. So I am writing here difficult. It means more energy is required to pair. Hence, the next electron enters into higher energy, but not paired. Very, very important. No pairing. Round it. No pairing. No pairing means high spin complex. High spin complex only possible in tetrahedral complex. Low spin complexes are very, very rare. Textbook question. Once again, I will repeat. In tetrahedral complexes, low spin complexes are very rare. Why? Reason. Delta T is equal to 0.45 times to the of delta naught. Delta T less than that of delta naught. This indicates splitting energy less in tetrahedral. That means pairing energy is more, opposite one. Pairing energy increases means difficult to pair the electron in the next level. That's why electron will never pair, enters into higher energy level. Obviously all are unpaired electrons. That leads to high spin complexes only possible, but not low spin complexes. Clear it is? So this is about tetrahedral complexes crystal field splitting, which is reverse to that of octahedral complexes indicated by delta T. It is reverse because the reason is direction of approaching of ligands in tetrahedral complexes. Now, drawbacks in CFT, crystal field splitting theory. The drawbacks are, actually the ionic bond they assumed as a ionic bond between the metal and ligand. But practically it is not ionic bond, it is a coordinate covalent bond. That is the first drawback. Second one, so few ligands in a spectrochemical series kept and acting as a strong field ligands. But those also few ligands as per that series cannot act as a strong field, they can act as a weak field. It means there is a problem as per the series. If you decide as per the series, practically there is a problem. Strong field may be weak field may be strong field. Few more drawbacks are there. You will see drawbacks of CFT. Students, drawbacks or limitations in CFT. It explains successfully the formation of complex compounds, structures, color, magnetic properties. But ligands are assumed to be point charges, especially negative ligands are assumed to be point charges. Obviously, ionic ligands have greatest splitting effect. If ionic ligands assumed as a point charges, so point charges means negative charge which must be located to the central atom. It has a greatest repulsion, nothing but a splitting effect. So but ionic ligands like fluorine, chlorine, bromine, iodine, fluor, F minus, Cl minus, Br minus, I minus, we have written at the low end of a spectrochemical series. I minus less than, F minus less than, Br minus less than, Cl minus less than, like that. Less than means lowest splitting effect. But as per the assumption, it should be highest splitting effect. It means you need to write the right side, but as per the spectrochemical series we have written left side, it means lowest splitting, but practically it is highest or greatest splitting effect due to the point charges. That is not explained. The ligands are assumed to be point charges. It follows that ionic ligands have greatest splitting effect. But ionic ligands structurally found at the low end of a spectrochemical series. But actually these must be located at which one? High end, which means high splitting effect. It does not consider a covalent character of a bond between the central metal atom and the ligand. It means as per CFT, the bond between the ligand and central atom is assumed as ionic bond, electrovalent bond, but not as a covalent bond. But practically it is a covalent bond, but not ionic bond. These are the drawbacks of CFT. Students, with this crystal field splitting or crystal field theory completed, we will discuss the next topic in our next video.